Start to record. And we can slowly start. So welcome everybody to this day seminar series Instinct Phenomenology. Today we have the pleasure to have two speakers, Gabriele Casagrande and Jesus Huertas. And our first speaker will be Gabriele Casagrande from Paris, who will talk to us about the massive spin-2 supermultiplet and its unique coupling to supergravity. Gabriele, please, you may start.
Okay, thanks Adriana, and thanks everybody for being here in the audience, and thanks also to Muldrow and Hayu, the other organizers, for the invitation to speak. Today I'm talking about a work I've been doing with my group here in École Polytechnique. So Guillaume Bossard, Emilian Dudas, who is my PhD supervisor, and Adrian Lotti, and the topic is, as the title says, massive spin-2 particles and their coupling to gravity in the presence of minimal supersymmetry. So the plan of the talk is the following. I will start with some introductory facts which motivate the work about the coupling of a single massive spin to gravity, and I will continue with the actual work. So I will introduce a supermultiplet for the massive spin-2 field, an object called the supercurrent superfield, which we will use to build this coupling to gravity, and I will then argue why this and in which sense this coupling to supergravity is actually unique, and then I will conclude. So I will start saying that despite having proven results and exact results is very difficult, it has been proposed that two scattering amplitudes of massive spin-2 particles coupled to gravity should satisfy this Froissart-like bound, meaning that the amplitudes cannot grow faster than s squared for t variable fixed. Earlier, the relevance of this s square bound was already present in this earlier work of Schwarz, in which massive spin-2 fields were analyzed in the context of a discretized extra dimension. But the main claim for this to hold was in this paper by Choudhury et al., in which they were calling this classical Regge growth conjecture, and they were giving several motivations for this to hold. And similar ideas about the coupling of a single spin-2 to gravity were also explored in the context of the Swampland program. And in particular, these authors suggested the impossibility of having a parametric mass gap of one single massive graviton to a tower of states. Further works about this bound and the Swampland conjecture can be found here. So what is the actual situation? Massive spin-2 amplitudes were analyzed in the literature. We have that the simple Fierz-Pauli theory coupled to gravity. Fierz-Pauli is the theory of massive spin-2 fields. The amplitude grows as s to the 5, and deformations can improve the situation up to s cubed. And the same happens if one introduces lower spin fields like spin-1, spin-2, and even higher derivatives. This was proven in this series of papers. Essentially, the amplitudes always grow at least as s cubed, meaning that they are outside the conjecture bound s squared. Of course, if one does not have a single spin-2, but rather a tower of states, the situation improves. And the example in which we can see this is the Kaluza Klein theory. If one reduces 5D gravity, for example, to 4D, on the orbifold, one gets further couplings, in particular, not only the coupling to gravity, but a coupling to the radion mode, to the higher tower of massive spin 2, and gets also some contact terms, which modifies the amplitude and improve its strength and lower it to actually increase it to order S, meaning that the theory is unitary in the sense of the bound proposed before. And of course, this is no surprise, since the 5D theory is, of course, well defined. The compactification has to be fine as well. But for this, one has to keep the full tower of massive spin 2 fields. And a natural question that arises is that, is this the only possibility to have a reliable theory of massive spin 2 fields in 4 dimensions? To get information about this, one would like to probe the couplings of the spin 2 to gravity without relying on any explicit Lagrangian. And this was also the perspective taken in these recent papers, but the way they were analyzing the theory was based on on-shell amplitudes techniques. Instead, in my work, we asked the help of supersymmetry, and we use a tool called supercurrent superfield, which I introduce later on. And with this, we are able to probe this essentially this 3-point function, so the coupling of two massive spin 2 to gravity. So in order to perform this analysis, the first ingredient one needs is a multiplet that includes the massive spin 2 field. And the way to obtain it is, for example, reduce 5-dimensional pure supergravity on the orbifold S1 over Z2. And it's simple to see that if one starts from 5D supergravity with this field content, so the Funfbein gauge field and to get Majorana Gravitini, and takes the reduction on this orbifold, which breaks supersymmetry from n equal 2 to n equal 1, the field content that one has is the supergravity multiplet in 4 dimension coupled to a chiral multiplet in the massive sector, while the massive modes organize precisely in the degrees of freedom of a multiplet for the massive spin 2 field. So the way to get the actual rules for this multiplet is very standard, and I'm going to review this very fast. One starts from the algebra of 5D supergravity, and again, since we are interested in this 3-point function, it's enough for us to work at the linearized level, meaning that we will keep non-linearities in the transformations only when the metric field is involved, and we will neglect all the rest. And the second ingredient is then an ansatz for the compactification, which is again very standard, and I'm showing it here. One plugs this into the previous algebra and gets some rules for the 4-dimensional decomposition. The following step is then to expand this field in modes along the compact interval, the compact dimension, and some of the fields will go then in the expansion with cosines and some of them with sines. And here I'm giving an example on the gauge field. And this is all very standard, of course. And the last step which I wanted to highlight here is that after doing this expansion in modes, one has to combine them into what are called the Stueckelberg decomposition of the fields. And this is very standard with massive gauge fields. It's a way to build to build the proper number of degrees of freedom for such massive fields. If one does this and neglects all the non-linearities, one ends up with the following rules, which one can abstract from and decouple from the actual KK reduction. And these rules describe the on-shell multiplet for the massive spin 2 field at the linearized level. And to our knowledge, we didn't find this transformation in any previous work. So the multiplet contains a massive spin 1, 2 Majorana Gravitini, or rather 2 Majorana spin 3 halves, and spin 2, all massive. And these are the rules relating them. Once the multiplet is found, we then go on and study the coupling of such multiplet to gravity, or rather in this case to supergravity. And the way to do it is through this object called the supercurrent. The supercurrent appeared in the very early days of supersymmetry, actually, and it's a very simple but super powerful idea. And it is that in a theory with supersymmetry, the currents of the theory stand themselves in a supersymmetric multiplet. These currents, I call this multiplet J, and these currents are an axial current, the current associated to supersymmetry, the stress energy tensor, and this is the minimal content, if you want, of these multiplets, which can then be closed in several ways. You can look up in the references all these different ways, but the way we choose in our work is to close it through an additional antisymmetric field, x mu nu. All these supercurrent multiplets are what are called linear superfield, so they satisfy this kind of constraint. When going from rigid supersymmetry to local supersymmetry or other supergravity, this multiplet have a natural interpretation. This is the multiplet containing the current associated to the gauge theory represented by supergravity. And it's very clear it's very simple to build the minimal coupling Lagrangian, where these currents are coupled to the correspondent gauge field. So the stress energy tensor coupled to the metric field, the supersymmetry current associated to the gravitino, and the extra two element of the multiplet are actually coupled to off-shell fields for the supergravity theory. And for those who know, this is what is called new minimal formulation of off-shell supergravity. The supersymmetry transformation relating the member of the multiplet are shown here. And the important thing to remember is that the axial current transforms into the supersymmetry current, and the supersymmetry current transforms into the stress energy tensor, which we are actually interested in. So having built the supermultiplet for the massive spin-2, we have, in order to find its coupling to supergravity, we can construct this object. And to do so, we start from the simplest element of the multiplet, which is the axial current, for which we have a natural ansatz, which is this formula, based on the fact that the axial current under consideration is associated to the R-symmetry of the theory. Okay, I call it automorphism of the algebra, but it's an actual R-symmetry. And starting from this, we can apply supersymmetry transformation and build all the rest of the multiplet. So the supersymmetry is the next in line and takes this form, which is not too important here. What is important is the next step. Taking a second supersymmetry transformation, one gets the stress energy tensor. This was a technically involved step, and the resulting tensor takes the following form. We have the kinetic sector associated to the kinetic terms of the Proca field A mu, the Rarita-Schwinger fields psi mu and chi mu, and the Fierz-Pauli, if you want, field H mu nu, so the universal part. But we find corrections to this. We find two terms, which I called d squared of G and dB, which are actual improvements to the kinetic stress energy tensor. Improvements in the sense that they do not modify the conserved charges associated to the tensor. Because of peculiar symmetries of these G and B tensors, if you want, their divergence is trivially satisfied. So they do not modify the conservation and the currents. And the improvements we find are of two different types. The first one, associated to the operator I call G, can be interpreted in the would-be Lagrangian as a non-minimal coupling to the Riemann tensor. And this is perfectly fine. It's a non-minimal coupling, which is diffeomorphism invariant, and well, they were already discussed in the original paper on improvements by Callan, Coleman, and Jakim, and they are very nice and a non-trivial thing to find. On the other hand, the B improvements are again non-minimal couplings, but not to the Riemann, but to the Christoffel symbol, to the Levi-Civita connection. And as we all know, the Levi-Civita is not a diffeomorphism invariant tensor. This means that These coupling in the Lagrangian are not diffeomvariant. These are not diffeomvariant operators. And after thinking a lot about this, we conclude that there's nothing one can do. These terms do not define consistent couplings to gravity because of this. So this poses a problem which one needs to solve in order to answer the question whether a coupling to gravity of this massive spin-2 supermultiplet is actually possible. And we will see shortly how it is possible to solve this problem, but there is a unique way to do it. We have to get rid somehow of these bad improvements, as I will call them. And the way is to modifying our starting point. So add improvements then to the starting axial current itself. I call these improvements delta J mu, and they can be written in this form, where L is an antisymmetric tensor. And so that one can see that they do not spoil the, as I said before, the conservation and the charges, because its divergence is trivially satisfied. We have then to figure out the most general ansatz describing this improvement to the axial current. And it turns out that the requirement of consistency of this improvement with the structure, with the setup we are studying, namely to behave with the right parity for J mu, to define a correct multiplet, together with the condition that these improvements do not introduce operators with more than 4 derivatives. All of these requirements constrain very much the expression for these improvements, and constrains to 3 operators, 1 bosonic and 2 fermionic ones, which I dub B for the bosonic, F1 and F2 for the fermionic. This is the most general improvement to the axial current one can build. And the idea is now to study the contribution of these operators to the resulting stress energy tensor, and possibly fix these 3 coefficients to remove the bad improvements from the stress energy tensor, which I stress, it's a way to impose diffeomorphism invariance in the correspondent couplings to gravity. So one can do this computation, which is again non-trivial from the technical point of view, and the final result is the following. The first bosonic operator, the bosonic operator and the first fermionic one introduce new independent bad improvement terms of the same type of the previous one, but new. So they if you want, they modify the theory in an even worse way. And one has no choice but to discard them from the ansatz. Otherwise, I mean, it's not solving the problem, it's actually making it worse. On the other hand, the second fermionic operator produces a bad improvement, which is exactly proportional to the original one. And one, therefore, has a unique solution. This is the sense in which I mean my uniqueness, as a unique solution for these coefficients, which kills all the bad improvement terms from the resulting stress energy tensor. The corresponding axial current takes this form and leads, therefore, to the stress energy tensor, which is unique in the sense of having no bad improvements, and it's unique up to 4 derivatives. This tensor is again given by the kinetic sector introduced before, and by a peculiar non-minimal coupling to the Riemann tensor, which involves operators coupling all fields. So we have a term quadratic in the spin-2, a term quadratic in the spin-1, and this is the sector which contains the 4 derivatives operators, a term mixing the 2 bosonic fields, and a fermionic term. So this is the main result of our analysis. And again, it's unique. I'll stress this. It's unique up to 4 derivatives in the sense that it's the unique solution for a supersymmetric and diffeomorphism invariant coupling to supergravity for this massive spin-2 supermultiplet. We then looked at the 2x2 scattering amplitude mediated by the graviton in this resulting theory. the stress energy tensor takes this form. This is the improvement involving two massive spin-2s. And the result is that the amplitude associated to this amplitude grows as S cube. So we are in agreement with the earlier analysis of these papers, which already show that this was the best one can do, modifying the field's Pauli theory. And of course, this alone has no hope to fall into the required bound conjecture by the papers I mentioned in the beginning. A natural question that arises at this point is, of course, since we found only one theory, where is Kaluza Klein? We expect somehow our analysis to capture the Kaluza Klein reduction, and we have somehow to understand if a relation holds between the two. To have an hint on this, which is still something we don't fully understand, we computed the difference between the amplitude in our setup and the amplitude given by the KK reduction, which was computed in these papers. And we found that the difference is local in the scattering parameter S. The fact that it's local suggests the possibility that that this difference can be realized in terms of contact terms and not by a interaction mediated by the graviton. And the way that one could get these contact terms is, for example, integrating out the tower of states coming from the reduction and potentially involving also a field definition of some sort, probably non-local, to get this infinite series of higher derivatives, which we prove it's unique at the fourth derivative level, but we suspect it's unique also to higher order in the number of derivatives, to get this, to interpret this difference and get the equivalence with the KK theory. So I reached the conclusion of my talk, which I now summarize. We were interested in studying the coupling of massive spin-2 fields to gravity with the help of supersymmetry. And to perform this analysis, we determined the massive spin-2 supermultiplet at the linearized level. We then built and constructed the associated supercurrent superfield J, as I described before, and we used supersymmetry and diffeomorphism invariance to study this coupling and show that this coupling to supergravity is actually unique. And we also studied the amplitude associated to this tensor, and we proved that its growth is of order S cube. As I highlighted in the very end, the future directions are, of course, meant to understand the relation between our theory and the Kaluza Klein reduction. And the straightforward step is to actually compute the full reduction of 5D supergravity to understand if integrating out the higher tower and performing some field definition can actually reproduce our pattern. And in order to understand the full structure of the improvement we find, it would be also interesting to study further 2x2 scattering amplitudes, for example, of the massive spin-1 field in U. Another interesting extension of the work is to move away from the new minimal of shell supergravity, or that we were somehow using, or rather using a different supercurrent multiplet. For example, the one associated to what is called old minimal supergravity, and it essentially giving up on the hypothesis of a conserved axial current, which may give new intuitions of what is going on from the 4D point of view. And okay, this is the end of my presentation. I thank you all for the attention.
Thanks a lot very much for this very nice talk, Gabriele. Let's thank Gabriele maybe through the. If there are questions, please just unmute yourself and speak up. Or you can raise your hand in Zoom.
I don't know how to raise my hand, but can I?
Please, Alessandra.
Since I'm not cutting anyone, just a clarification. So until you can prove explicitly any contact with Kaluza Klein reduction, can you say something about these realizations as low energy theory from some string theory construction?
I'm sorry, can you repeat them? I'm not sure.
Yeah, sorry. I was wondering, like, can you already say something about these massive supergravity multiplet coming from string theory, for example, for some particular low energy model?
It means that you want to, you're asking me if I can really somehow connect this 5D supergravity to a string theory, a full string theory reduction, you mean?
Yes.
Or,
maybe not straightforwardly top-down model, but like, are there hints that you can start realizing also some low energy string theory models?
For sure, in string theory, you expect probably this kind of multiplets to arise because you expect all of the spins to be there, but I don't know of an explicit construction. One should figure out somehow some, I guess, orientifold compactification to break supersymmetry down to. So it would be interesting if there's a possibility to do it straightforward to 4 dimensions, I guess, and then you get maybe some different structure for the multiplet, although I'm not sure of this. But a straightforward top-down construction, I don't know about it.
Okay, yeah.
That reproduces this simple setup. I mean, that there are probably plenty.
Yes, because there are models where like you can have regimes where you can see some massive graviton. So it would be. All I'm saying is it's going to be very interesting to try to understand more about this. So from
I'll keep this in mind. Thanks.
Thanks. Thank you.
Any more questions for Gabriele? All right. Okay, if not, you will also have the chance to ask Gabriele questions after the second talk finishes, but now we can proceed to the talk by Jesus. So if you could stop maybe sharing your screen. Thank you very much once again, actually.